Hello, I'm DJ, a final year PhD student from the University of Washington. This work was done as part of my summer internship at Microsoft Research, looking at sound accessibility in virtual reality. An example of sound accessibility is shown here in the background image, which shows text representation of water flowing and footstep sound from a popular VR game, Minecraft. Okay, so let's begin with an introduction. Sound is a very critical component of the VR world. It can provide critical information, such as approaching enemy footsteps, can increase realism, such as through a wind blowing sound, or add aesthetic to a VR app, such as using a water spill sound. However, for many deaf and hard of hearing people, these sounds and the information they convey are not accessible, which may limit the VR experience. They may miss critical cues in games or may not feel fully immersed. We are exploring how to make sounds in VR accessible to DHH people. But typically, we contribute a design page to map sounds to visual and haptic feedback in VR and to exploration of the design page, using it to contextualize the state of the art on sound accessibility and develop new VR sound accessibility prototypes. Before I go into details of this, let me quickly cover some relevant past work. Researchers have explored visual and haptic substitutes of everyday sound for DHH users, but this approach has not been examined for virtual reality. Now, VR is a radically different environment containing both the fictional world and a exaggerated representation of the real world. Some VR games have begun incorporating initial accessibility features for DHH people, but these are one-off commercial efforts which have not been formally explored in the literature. Our focus instead is on making mainstream VR accessible, which leads to lower development costs, increased availability, and better social acceptability over specialized experiences. Okay, so coming back to the outline, let's start with the design page. Our design page contains 9 dimensions to map different types of VR sound and their characteristics to visual and haptic feedback, 3 each for sound, visual, and haptic. Let's start with the sound. The dimensions of sound were inspired from a recent DISC 2021 paper, which actually related a taxonomy of sound in VR. This paper gave us 2 dimensions. The sound source would represent the object in VR that sound is emanating from, such as localized speech, non-localized speech, and so on. And the sound intent would represent the intended functionality of the sound, such as for conveying critical information, increasing realism, and so on. These 2 dimensions together articulate all sound in VR comprehensively. But to map the sound to visual and haptic feedback, we added a 3rd dimension called sound characteristics containing the basic constituents of sound, such as identity, location, loudness, and so on. So we have these 3 dimensions of sound. Now these sounds need to be converted to visual and haptic output for accessibility. So we needed some way of representing the visual and haptic feedback as well. We articulated 3 dimensions under each containing the form factor dimension, that is the device on which the feedback is delivered, such as the headset, smartphone, and room scale, and so on. The location at which the feedback is delivered, such as for the haptic case, palm, arm, torso, etc. And similar to the dimension of the sound, the basic constituent or the element of the feedback, such as in case of haptic, intensity, timbre, rhythm, and so on. Now, so these are the 9 dimensions of a design space. Our design space is then just set up all possible mapping from our input dimensions of sound to the output visual and haptic feedback dimension. Let's consider an example. Say we have this sound accessibility feature. a speech caption appearing at the bottom of the screen. So in our design space, this will be represented as non-localized for sound source, for critical information sound intent, identity for sound characteristics, map to the visual feedback, headset for visual form factor, overlay for visual location, and the text for visual element. So this is the summary of the mapping. Another example includes localized caption for each speaker in space. This can be mapped as localized speech for sound source, for critical information for sound intent, and identity, that is the spoken content for sound characteristics, map to headset for form factor, cue, and text because captions are shown. So you can see how someone can also generate new mapping by using a different permutation of categories within each dimension. So that concludes our design space section. Moving on to the next section, exploration of our design space. A successful design space should be able to contextualize prior mapping and also generate new mapping. Towards the first goal, that is contextualizing prior mapping, we investigated recent VR apps and games containing accessibility features for DHS users, for example, caption, sound direction indicators, etc. In total, we analyzed 78 apps. A total of 114 sound to visual haptic feedback mapping were found in this app, and a design space successfully contextualized all these mappings. This meant that our design space can uniquely and adaptively map down the visual and haptic feedback. So by now, we had a comprehensive list of sound to visual haptic feedback designs that have not been explored before. Informed by the design, we then use the design space to develop new sound to visual haptic feedback mapping and instantiated this mapping through VR sound accessibility prototypes. These prototypes were developed through a multifaceted process in consultation with VR developers, sound designers, and were vetted by 2 DHS members of HAM. In total, we generated 6 prototypes, 4 visual and 2 haptic. Let me show you a quick video of what the prototype looked like. So that went by a little fast, but you got an idea. The important thing is that these prototypes are generalizable and can be incorporated by developers into any new or existing VR app using our core module to provide sound accessibility. These modules automatically extract the relevant sound information from the app, and the visual or haptic rendering can be customized by the developer. To access the usability and generalizability, we also briefly evaluated the prototype with a target DHS users as well as VR developers who augmented these prototypes to their own app. Results were promising, but more details are left for the paper. So in summary, our work contributes a design space for developing visual and haptic representation of VR town to support DHH users, characterization of town accessibility features in recent VR apps and games, and generalizable VR prototype instantiating novel town to visual haptic mapping. So where do we go from here? Further prototype exploration. Our prototype investigated a single town to visual and haptic mapping in isolation. But in VR, multiple towns can occur simultaneously. And so how best to combine this prototype without overwhelming the user is an open question. Second, personalization. Our prototype can be sufficiently personalized by the developer to choose their app name. However, it may then be desirable for end users too to customize the prototype according to the needs and hearing abilities. Example of what sound frequencies are visualized. And so how and what end user customization should be provided needs to be explored. Other domain, finally, while we chiefly focus on DHS users, our work has applications for other domains as well. For example, there may be cases when you may not be wearing headphones in VR and would want to have alternative sound visualization for any misinformation. Right? Sound feedback also has applications in other areas as well, such as in appliance repairs or ecological surveys. All these need to be explored. So in conclusion, I'd like to leave you with an important statement. Too often, accessibility is considered as an afterthought while designing technology. But since VR is a new and emerging technology, we're at an important point in time when we can still incorporate accessibility into this emerging medium from the very beginning. Some researchers have begun to consider making VR accessible for people with visual and mobility impairments, but the needs of DHS users are as yet unexplored. In this work, we have provided the first comprehensive look at town accessibility in VR. And I'd like to call out to all researchers and practitioners to continue to enhance town accessibility in VR because it affects all of us. Thank you.